Let's continue where we left. Um, in this case, let's talk about the next thing right here. You will see after defining inputs and outputs, we need to define a counter. We'll explain the counter in SQL. Then we need to define two integers, period length and pulse length. Basically, the period length is our t variable and pulse length is t1. Graphically again, t1 and t are given over here. Um, this is t and this is t1. See, this is how it looks like. So let's move on to this one. This block over here is the um, always block that is used to increment the counter or to reset the counter. Let us explain this block. First of all, let us sketch our clock. Remember that a clock is nothing less than a train of pulses uh, with the width of, or better to save the period of 10 nanoseconds. Whenever a positive edge of the clock is detected, that is, whenever the clock goes from the low value to the high value, that is, this is the positive edge. Then this part over here will be executed. And notice over here that we have non-blocking statements. This statement will always run in the background. They will not the run sequentially, then will run basically in parallel all the time. So let's see what happens over here. So let's just skip this ad and move on to the video and see what's in there. Okay, so we are here. If the counter is smaller than the period length, then the increment the counter. This means the following. Since we defined the desired post-modulation signal to look like this, where this is basically um, T and this is T1. This counter will basically increase, and okay, and until we come here, that is until we reach the period length of 4000, and then the counter will simply reset. Okay, now we have a counter. Next, we need to produce a pulse feed modulation signal. So let's see how to do that. Keep in mind that counter goes from 0 to period length. Then it resets in the next period, and again it counts from 0 to the period length. So how to produce a pulse feed modulation signal? Basically, we can produce the pulse with modulation signal by using this code line. So this is code line is basically an if statement. If counter is smaller than pulse length, and the pulse length is given by over here, and let us graphically again visualize the situation. Okay, so this is our t that is period length, and this is t1, and this is our pulse length. So when a counter is smaller than a pulse length, that is when we are here. The value will be high if the counter exceeds the pulse length, then the LED value will be 0. So this is our LED. Um, and by using this simple if statement, we can produce a pulse with modulation signal in this code. So we are producing a pulse speed modulation signal with a period of 4 milliseconds and with a pulse width of 2 milliseconds. Now we can stop here and ask following questions. How did we calculate these values? That is, how can we transfer period length pulse length and our counter into seconds, well, it's quite straightforward. Um, we just have to keep in mind what is our period of clock of the system. In our case, that is 10 nanoseconds, and mathematically, that is 10 time 10 to the minus 9. Then you just need to multiply the clock period with the period length of your pulse feed modulation signal, and you can get the period of the post-fit modulation signal consequently. Since we have over here in our code, let's see that 4000s for our period length. Basically, we have 4 times 10 to the 5 multiplying 10 multiplying 10 to the minus 9, and that produces 4 times 10 to the minus 3. That is our 4 milliseconds. Similarly, we can compute the pulse width that is equal to 2 milliseconds. Obviously, we can change these parameters, via length and push length, to achieve desired shape of the pulse fed modulation. So from here, you can move on and you can continue your lab. So I think that is enough explanation. So carry on to your labs. Thank you.